Module E, Parametric Procedures. In this module, I'm going to introduce the class of parametric multiple testing procedures, which means procedures that are based on specific distributional assumptions. They're used in multiplicity problems arising in clinical trials with a known joint distribution of the hypothesis test statistics, and the first commonly used parametric procedure was introduced by Dunnett back in his seminal paper in 1955. This procedure is now known as the Dunnett procedure or a single-step Dunnett, and multiple extensions of this first Dunnett procedure have been developed over the years. Those procedures can be thought of as procedures from the family of Dunnett procedures. I will concentrate on those procedures in the only section in this module, and towards the end of the section I will briefly mention other approaches to constructing parametric procedures that have been used in clinical trials. Also, I've made multiple references to the FDA's draft guidance on multiple endpoints in clinical trials throughout this online training course, and I would like to mention here that parametric procedures are not discussed in this guidance, but what we need to realize, of course, is that multiplicity problems arising in the analysis of multiple endpoints are not different at all from problems that arise in other settings, which includes the setting of multiple dose placebo comparisons as an example 4, or multiplicity problems arising in multi-population trials as an example 5. And the EMA guideline briefly mentions multiplicity problems in trials with more than 2 arms in section 5. So once again, there's only one section, it's section E1, Parametric Multiple Testing Procedures. Let's begin with a summary of key properties of parametric procedures compared to non-parametric and semi-parametric procedures that we explored in modules C and D. As you remember, non-parametric procedures do not make any assumptions about the joint distribution of the hypothesis test statistics, and for Symes-based procedures such as the Hommel and Hogberg, known as semi-parametric procedures, the family-wise error rate is protected for certain types of joint distributions. So now let me contrast non-parametric and semi-parametric procedures with the class of parametric procedures we're going to study in this module. Parametric procedures make explicit distributional assumptions. For example, the underlying decision rules may be based on the fact that the hypothesis test statistics in the multiplicity problem of interest follow a multivariate normal distribution or, for example, a multivariate t-distribution. So the distributional assumptions are built into the decision rules, into the critical values. As a result, since they utilize more information, for example, they account for the correlations among the test statistics, parametric procedures are more powerful than their non-parametric and semi-parametric counterparts. This is an important conceptual difference, and as far as similarities are concerned, parametric procedures, just like non-parametric or semi-parametric, can be constructed using a single-step testing approach, which gives us single-step parametric procedures, and likewise, stepwise parametric procedures can be built for problems with a data-driven testing sequence or a pre-specified testing sequence. In fact, if we look closer at commonly used parametric procedures, we will discover that these procedures are, in fact, extensions to parametric problems of the non-parametric and semi-parametric procedures from Module C. For example, the single-step Dunnett procedure, which Dunnett proposed in 1955, is a parametric version of the basic Bonferroni adjustment. Then, assuming that hypothesis ordering is not fixed, it is data-driven, a step-down parametric procedure can be set up based on ordered p-values or ordered test statistics. It will be a parametric version of the Holm procedure, and it's known as the step-down Dunnett. And also a step-up parametric procedure, which is similar conceptually to the Hogberg, can be constructed. And you can guess that this procedure is known as the step-up Dunnett, because it also utilizes a step-up testing algorithm. So these parametric procedures define what I call the Dunnett family of parametric procedures, and we will focus on the first two procedures. To define these parametric procedures, we need to define a parametric hypothesis testing problem. And how is it different from hypothesis testing problems that we used in Module C or D to define other procedures? They're actually exactly the same. The only difference is that in parametric settings, we know something about the joint distribution of the test statistics. For example, here is a generic clinical trial with multiple dose placebo comparisons, which is designed to evaluate the efficacy as well as safety of several doses or several regimens of a new treatment compared to a common control. Let's say this will be placebo. Let us assume that the response variable is normally distributed or nearly normally distributed, and we will also assume for simplicity a balanced trial design, which means an equal number of patients across the treatment groups. We have seen the setting multiple times in this course. Example 4, based on the type 2 diabetes trial, is an example of a clinical trial with several dose placebo comparisons. In this particular case, there are 3 doses of a treatment and a placebo arm. So there are 4 arms in the trial, and there are 3 dose placebo contrasts or comparisons that are represented here by the arrows. We will assume the following underlying model in this clinical trial. It's a simple one-way ANOVA model, which means that the response variable, denoted by Yij, in each treatment group is a sum of the group mean, denoted by μi, and the normally distributed arrow, epsilon ij. And the first index in this model, the I index, is the group index, and 0 here denotes the placebo group. And the second index, j, is the patient index. J goes from 1 to n. And once again, we assume here a balanced design with n patients in each treatment group in this trial. So this is the underlying parametric model. The joint distribution of the responses is known, they are independent, and the marginal distribution is normal. And the parametric testing problem is defined in terms of the parameters in this model. What the sponsor is interested in this clinical trial is the mean treatment difference for each dose placebo contrast that are denoted by theta 1 through theta m. The sponsor is interested in testing the null hypotheses of no beneficial effect that are associated with those mean treatment differences. And if we assume that a positive value of theta indicates a beneficial effect, then the null hypothesis hi, as you see on the slide, corresponds to the case when theta I is less than or equal to 0. Those null hypotheses will be tested using a set of hypothesis test statistics denoted by T1 through Tm, and each one is based on the simple t-test, 2-sample t-test to be precise, and thus the test statistic Ti follows a t-distribution with 2 times n minus 1 degrees of freedom. And if we assume the null hypothesis, that is if theta I is equal to 0, then the test statistic Ti follows a central t-distribution, and the p-values are computed from this null distribution, from those central t-distributions, and they're denoted as before by p1 through pm. They're shown at the bottom of the slide. With this notation in place, let us revisit the Bonferroni procedure, which is the single-step non-parametric procedure. When I say single step, I mean that all p-values are compared to the same significance level or the same threshold. This threshold, the significance level, is chosen to guarantee that the family-wise error rate is no more than alpha. So if we assume that all null hypotheses are simultaneously true, then the family-wise error rate is given by this probability. It's the probability that at least one p-value is less than or equal to the adjusted significance level, and this common significance level is denoted by alpha tilde. And with the Bonferroni inequality, we can show that this probability is less than or equal to alpha if the adjusted significance level for each p-value is alpha over m. What is important to remember here is that we did not directly evaluate this probability, because this would have required knowledge of the joint distribution of the p-values. But instead of this, we simply used an upper bound for this probability based on the Bonferroni inequality. It's a very important point here. Dunnett procedure. In the context of the multiplicity problems that we considered in modules C and D, we could not evaluate the probability which defines the family-wise error rate, simply because we did not know the exact joint distribution of the p-values, or equivalently, the joint distribution of the hypothesis test statistics. For example, if we look at example 1, that was the prostate cancer trial example with two endpoints based on progression-free survival and overall survival, we may be able to find an asymptotic joint distribution of the associated test statistics. Those will be log rank statistics. But since we don't know the correlation between the test statistics, we cannot find the exact value of the probability that defines the family-wise error rate. But on the other hand, if we happen to know the joint distribution of the test statistics, which is, by the way, the case in this setting when we consider clinical trials with several dose placebo comparisons, instead of relying on this crude upper bound based on the Bonferroni inequality, for example, we can directly compute the family-wise error rate for any given significance level, and we can use this knowledge to build exact multiple testing procedures, which is exactly what we're doing on this slide. The basic Dunnett procedure, the single-step Dunnett procedure, is a parametric version of the Bonferroni, which means that it's a single-step procedure in which a common adjusted significance level is used for all p-values, and this adjusted significance level is found by utilizing the joint distribution of those p-values. So we again assume here that the hypotheses of interest, h1 through hm, they're all simultaneously true, and therefore the family-wise error rate is equal to this probability. We can compute this probability for any value of the adjusted significance level, alpha tilde, and we can choose that adjusted significance level in such a way this probability exactly equals alpha. It's not going to be less than or equal to alpha, it's going to be exactly alpha. In this case, we don't need to use upper bounds anymore. Another way to present the same mathematical argument is to define the decision rules for the null hypotheses in terms of the test statistics rather than p-values. Then find a common adjusted critical value for those test statistics. In this case, alpha is equal to this probability that you see on the slide right now. It's the probability that at least one test statistic is greater than or equal to the common adjusted critical value. It is denoted by C, and therefore this probability is the probability that the uppercase T is greater than or equal to C, and the uppercase T is the maximum test statistic. Charles Dunnett derived the null distribution of the maximum test statistic when the individual test statistics follow a multivariate t-distribution. It is known as the Dunnett distribution, and it is characterized by two parameters shown at the bottom of the slide. The first parameter, m, is the number of hypotheses in this multiplicity problem, and nu is the number of degrees of freedom. This is the parameter that also depends on the sample size. Here is a bit more formal definition of the Dunnett distribution for a multiplicity problem arising in a clinical trial with multiple dose placebo comparisons. There are actually, we assume here that there are m dose placebo comparisons, and therefore there are m test statistics. And this is the maximum of m test statistics, where each one of those individual statistics follows a central t-distribution. The maximum of those test statistics would then follow a multivariate t-distribution. And it's also important to add that they are equally correlated with a common correlation coefficient, rho, which is equal to 0.5 or 1/2 in this case, because we're dealing with a balanced design. The adjusted critical value C used in the Dunnett procedure is then simply computed as the 1 minus alpha quantile of this Dunnett distribution, and it's given by this formula. Given the adjusted critical value C, the decision rule of the single-step Dunnett procedure is shown at the bottom of the slide, and the single-step procedure rejects the null hypothesis Hi if its test statistic exceeds the resulting adjusted critical value C. The type 2 diabetes trial with the parameters shown in this table. This set of test statistics will be labeled Scenario 5, will be used to illustrate the process of computing the critical value of the Dunnett procedure. And very briefly here, we've used similar summaries of study results before. The only difference between this particular table and tables that we used in modules C and D is that here, instead of p-values, we compute test statistics. For example, the test statistic for the comparison between dose 1 and placebo, in this case, is equal to 2.64. And likewise, if we look at the comparison between dose 3 versus placebo, the associated test statistic is 2.31. We need to make assumptions about the common sample size. We assume here that the common sample size per group is 90 patients, and also assumptions about the pooled standard deviation. Let's assume that this quantity is equal to 1.6. The plot shown on the slide 17, is very similar conceptually to similar plots that we have used before to summarize the results of clinical trials and illustrate decision rules used by multiple testing procedures. The only difference here is that what we see on the vertical axis is the test statistic for evaluating the amount of evidence against each individual null hypothesis, and before we used to have one-sided p-values on the vertical axis. The critical value of the single-step Dunnett procedure is equal, as we said, the 1 minus alpha quantile of the Dunnett distribution. In this case, the parameters of the Dunnett distribution are given by 3, that's the number of comparisons, and the number of degrees of freedom is 356. It's quite easy to compute from the common sample size and the number of comparisons. And since the one-sided alpha here is set to 0.025, we can derive the critical value, this adjusted critical value for each individual test statistic in this multiplicity problem is 2.36. You see it at the bottom of the slide. And with this critical value, it's represented by the horizontal dotted line. We see that only one of the 3 test statistics is above this threshold, which means that the basic single-step Dunnett procedure rejects only one null hypothesis. In this particular case, it's the hypothesis H1. Therefore, our conclusion is that after the Dunnett-based multiplicity adjustment, only dose 1, the high dose, shows superiority compared to placebo. For the sake of a quick comparison, this slide shows the critical value of the Bonferroni procedure in the type 2 diabetes trial under the same set of assumptions. This critical value is found from the univariate t-distribution. You can see the formula at the bottom of the slide. And what's important to do here for us is to take the alpha level and divide it by the number of comparisons, which is 3 here. And this results in the Bonferroni adjusted critical value of 2.42. It is obviously slightly greater than the Dunnett critical value from slide 17, and therefore, by using a parametric approach, we gain power, but in this particular case, the gain is quite small simply because there is just simply not enough multiplicity. The burden of multiplicity is not high enough in this particular trial to be able to experience large improvement. With more null hypotheses and higher correlations among the individual test statistics, one should expect to see a larger power advantage when comparing parametric procedures and, for example, non-parametric procedures. To go over the key properties of the Dunnett procedure we have just defined, what's important for us to remember is that this is a parametric procedure and it controls the family-wise error rate in a parametric setting when the hypothesis test statistics follow a known distribution. In this case, this would be a multivariate t-distribution. An example would be a clinical trial with multiple dose placebo comparisons when the response variable is normally distributed. But of course, it's natural to ask this question: what if the response variable, the primary endpoint, is binary, or perhaps it follows some other distribution, which is not normal? The good news here is that the Dunnett procedure can also be used in those settings, and it generally performs quite well with non-normally distributed responses, provided the sample size per group is large enough, and by large enough in this case I mean about 30 patients or more per group, which will clearly be the case in all confirmatory clinical trials, and this condition may also be satisfied in phase 2 trials. As far as power is concerned, the Dunnett procedure is a parametric procedure, and you would not be surprised to find out that it is uniformly more powerful than the Bonferroni procedure, which means that the Dunnett always rejects all hypotheses rejected by the Bonferroni, and sometimes it will reject additional hypotheses. And even though this power gain is sometimes relatively small, we should definitely take advantage of this feature. It's a free lunch. We end up with more power simply because we use a more efficient statistical approach. Step down Dunnett procedure. So far, we have defined one procedure from the Dunnett family of parametric procedures. It is the most straightforward, single-step procedure, which serves as an extension of the basic Bonferroni. And on this slide and the next few slides, I will show you that other non-parametric or semi-parametric procedures are naturally extended to this parametric setting. For example, if we assume that the null hypothesis is of no effect in a clinical trial with, for example, several dose placebo comparisons, we assume that those hypotheses are not ordered. We deal with the case of a data-driven hypothesis ordering or data-driven testing sequence, and it is quite easy to construct a parametric step-down procedure, which looks very much like the Holm procedure. It is essentially just a step-down Dunnett procedure, and it's a parametric version of the Holm in the sense that it tests the null hypothesis using a step-down testing algorithm, sequentially beginning with the smallest p-value or equivalently with the largest t-statistic. The notation I'm going to use here is similar to the notation we used for ordered p-values. It's the parenthetical notation to define the ordered test statistics. The test statistic on the left is the largest test statistic, and the test statistic on the right is the smallest test statistic. This slide defines the general decision rules of the step-down Dunnett procedure. I will concentrate on a couple of key points here that help us make a connection between this parametric step-down procedure and the non-parametric step-down procedure, specifically the Holm procedure. First of all, if we take a look at step 1, we notice that the largest test statistic, or the most significant test statistic, is examined in the first step. For the Holm procedure, the decision rule for the first hypothesis in the sequence was formulated in terms of the most significant p-value, and here it is conceptually exactly the same approach. It's just we have switched from p-values to test statistics, but everything else is exactly the same. Secondly, the critical value for the first hypothesis, which is denoted by C1, is in fact the critical value of the basic single-step Dunnett procedure, which again parallels the fact that for the Holm procedure, the first adjusted significance level is simply the significance level that would be used in the basic Bonferroni procedure. And another quick point I would like to make here is that when we introduce the step-down algorithm for the Holm procedure, in this step-down algorithm, the hypotheses are tested at successfully higher significance levels, which results in power gain compared to the Bonferroni procedure. And in this particular case, if we take a closer look at this step-down procedure, we see that each hypothesis is tested using a successfully lower critical value. And specifically C1 is greater than C2, which is greater than C3, and so on. And thus it is getting easier to detect significant differences toward the end of the sequence, and this results again in the power gain compared to the step-down Dunnett procedure. And in fact, the step-down Dunnett procedure can be shown to be uniformly more powerful than the single-step Dunnett, just like the step-down non-parametric procedure, which was the Holm, is uniformly more powerful than the non-parametric single-step procedure, which is the Bonferroni. At this point, it will be appropriate to give you an example and walk you through the step-down testing algorithm used in the step-down Dunnett procedure. And I will use the same set of test statistics as before. This example is again based on example 4. The only difference here is that we need to introduce the ordered test statistics, and you can see those ordered test statistics defined below the table. When we apply the step-down Dunnett procedure, we will need to go through a series of steps because this is not a single-step procedure anymore. Step number 1, the step-down Dunnett procedure begins with the first hypothesis in the sequence. That's the hypothesis corresponding to the most significant test statistic. You can see here that the adjusted critical value, C1, is exactly the same value that we derived when we talked about the single-step Dunnett procedure. C1 is equal to 2.36. It is represented by the horizontal dotted line in this plot, and the orange dot on the left, which corresponds to the largest test statistic, is clearly above this threshold, and therefore we conclude that the step-down Dunnett procedure rejects the first hypothesis in the sequence. In step 2, a lower critical value is used, and to understand why this happens, recall that one hypothesis has already been rejected. That happened in step 1, and therefore we kind of pretend here that there are only 2 tests or only 2 hypotheses left in this problem, and therefore when we compute the adjusted critical value for the second hypothesis in the sequence, it's denoted by C2, and we apply the Dunnett critical value, the number of comparisons is set to 2 instead of 3, and the resulting test statistic, denoted by C2, is equal to 2.22. Once again, it's represented by a horizontal line in this plot. You can see that Since this adjusted critical value is lower compared to C1, now the second hypothesis in the sequence can be rejected because the orange dot that corresponds to that hypothesis is above the threshold. However, if we were to apply the single-step Dunnett, this hypothesis would not have been rejected. And now finally the critical value. In step 3, this critical value is computed as if there is no multiplicity in this problem. The number of hypotheses is only 1, and we see that the first parameter in the formula used for computing the adjusted critical value, C3, is set to m minus 2, which is 1, and therefore the resulting adjusted critical value is only 1.97. This critical value is much lower than the critical values used in steps 1 or 2, but despite this fact, the test is not significant because the test statistic is simply not large enough relative to this lower critical value. And the conclusion is that the step-down Dunnett procedure cannot reject the last hypothesis in the sequence. Now to summarize, the step-down Dunnett procedure controls the family-wise error rate under the same parametric assumption as the single-step Dunnett. Specifically, the test statistics follow a multivariate distribution. And as I said a minute ago, since the step-down Dunnett procedure relies on an efficient step-down testing approach, it is uniformly more powerful than the single-step Dunnett procedure. In addition to that, we can show that the step-down Dunnett is uniformly more powerful than the Holm procedure as well. Step-up Dunnett procedure. Here's another procedure in the Dunnett family, which can be used in problems with a data-driven testing sequence. It's a step-up procedure, which means that it's built using the same ideas, same principles as the Hogberg procedure that we discussed back in Module C. And specifically, the null hypothesis would be tested beginning with the smallest or least significant test statistic. It's a powerful procedure, but the problem is that it's based on a rather complicated algorithm, and currently there is no straightforward software implementation available for this procedure. And as a result, it's not used in clinical trial applications, and I'm not going to explicitly define this procedure. It will not be discussed further in this online training course. But for your general information, here is a quick summary of key properties of the step-up Dunnett procedure. The step-up Dunnett procedure is parametric, which means that it protects the family-wise error rate under parametric assumptions. It is uniformly more powerful than the Hogberg procedure, and in addition, it is uniformly more powerful than the single-step Dunnett procedure. But here is an interesting fact. It turns out that the step-up Dunnett is not always more powerful than the step-down Dunnett procedure. And as you remember from Module C, when we studied non-parametric and semi-parametric procedures, the step-up procedure, which was the Hogberg, was always more powerful than the step-down, which is the Holm procedure. However, this relationship between step-up and step-down procedures is not applicable in the world of parametric procedures. Other parametric procedures. We are done with the Dunnett family of parametric procedures. It includes, once again, a single-step procedure and two procedures for multiplicity problems with a data-driven testing sequence, the step-down Dunnett and the step-up Dunnett. However, in general, parametric procedures can also be defined for clinical trials with a pre-specified testing sequence. When there is a natural, clinically meaningful way of arranging the null hypothesis of interest, and if in addition the clinical trial sponsor has information on the joint distribution of those test statistics, instead of using the non-parametric fallback, which is a non-parametric procedure derived from the Bonferroni, the sponsor can consider its parametric version. And likewise, a class of parametric chain or graphical procedures can be developed, and they can be used in two different settings. For example, when the hypothesis ordering is data-driven or when it's pre-specified. And finally, at the very bottom of this slide, there's another class of parametric procedures with a pre-specified testing sequence known as feedback procedures. And procedures in this class have found important applications to clinical trials with multiple populations. For example, when there's a targeted subgroup in addition to the efficacy test in the overall population. Since we're ready for a summary, I will use this diagram to present visually the key properties of the parametric procedures we've introduced in this module and compare them to the key properties of the non-parametric and semi-parametric procedures from Module C. In fact, the three procedures represented by the three orange boxes shown in the top row of this diagram are the Bonferroni-Holm-Hogberg procedures that are examples of non-parametric and semi-parametric procedures. And in the bottom row, we see parametric procedures from this module. The single-step Dunnett, the step-down Dunnett, and finally the step-up Dunnett on the right. The six procedures are arranged in the order of increasing power from left to right and also from top to bottom. And as we said at the end of Module C, the semi-parametric procedures such as the Hogberg and Hommel are recommended when the joint distribution of the hypothesis test statistics is not fully specified. And by the way, if I could make a very quick comment here, the upper right box in this diagram actually represents both of those semi-parametric procedures. So we can think about it as the Hogberg and Hommel procedure included in within the same box. And the arrows in this diagram show that the Holm procedure is uniformly more powerful than the Bonferroni. The Hogberg/Hommel procedures are uniformly more powerful than the Holm. That's what we learned from Module C. And then in this module, I have introduced extensions of those three multiple testing procedures to a parametric setting for a specific joint distribution of the hypothesis test statistics. And by utilizing this additional distributional information, we gain power, and in fact, most of the time this power gain is uniform. So whenever we have to choose between the Bonferroni and basic Dunnett procedure, the Dunnett procedure, of course, must be selected. And further down the line, the step-down Dunnett procedure beats, in terms of power, the single-step Dunnett and the Holm at the same time. And what we have in the lower right corner of this diagram is the step-up Dunnett procedure. It is almost the best procedure on the slide. It gives us more power than the Hogberg, but as I explained a couple of minutes ago, a bit surprisingly, it is not guaranteed to be always better in terms of power than the step-down Dunnett. And in addition, since there is no simple way to implement the step-up Dunnett, the award in this category probably goes to the step-down Dunnett procedure. Software implementation. We're going to wrap up this module, and as we have done before in modules C and D, we're going to present software implementation options for the parametric multiple testing procedures introduced in this module. Slides 35 and 36 list available software implementation options for parametric procedures in SAS and in R. And although the single-step Dunnett adjustment is included in several SAS stat procedures, for example, proc mixed, there is really no standalone implementation of the single-step and step-down Dunnett procedures. And this is where the parproc macro comes in. Parproc stands for parametric procedures, And this macro computes adjusted p-values for the single step and step-down Dunnett procedures. And here I need to clarify that this function focuses on a common case of one-sided hypothesis testing problems in clinical trials with a balanced design, which means equal number of patients across the arms, and the hypotheses are assumed to be equally weighted. As far as our implementation options are concerned, we will use again the Mediana package and the adjust p-values function available within that package because it supports commonly used non-parametric, semi-parametric, and what's important in the context of this module, it also supports parametric procedures. Let me show you how to use the SAS macro and our function I introduced on slides 35 and 36 in the type 2 diabetes trial. This table, and we've seen it several times before, defines the test statistics for the 3-dose placebo comparisons in this trial. This is the information we need to apply a parametric multiplicity adjustment. And we also need to know the sample size per group, which is 90 patients. It is a balanced design, and the 3 tests are equally weighted, which means that we can go ahead and use the Parametric macro and adjust p-values function to perform multiplicity adjustments based on parametric procedures in this example. Beginning with the SAS macro, we need to specify the hypothesis-specific test statistics. These statistics are saved in the dataset called EX4. The dataset EX4 is passed to the Parametric macro along with the common sample size per arm. It is a required parameter, n is equal to 90 here, and the macro produces a dataset with multiplicity adjusted p-values. This macro, as I pointed out earlier, also supports the step-down Dunnett procedure, and the variable name in the adjusted p dataset, which corresponds to the adjusted p-values based on the step-down Dunnett procedure, is step Dunnett. This variable name is shown at the bottom of the slide. The output produced by the Parametric macro is presented on slide 40. Here we see a set of raw p-values computed from the test statistics that we specified earlier, and this set of raw p-values is accompanied by a set of adjusted p-values that were derived based on the single-step Dunnett procedure. Finally, very quickly, the adjust p-values function from the Mediana package can be called to implement several parametric procedures, including the single-step Dunnett and the step-down Dunnett. To show you how to implement the single-step Dunnett procedure, we need to first compute the vector of one-sided p-values from the test statistics. It's the vector p. This vector is passed to the function. The proc parameter is set to Dunnett adjust, and again the suffix adj indicates that this is a function that performs a multiplicity adjustment. And finally, the optional parameter par is used to specify the common sample size per arm, n is equal to 90 in this particular case. This results in the same set of multiplicity adjusted p-values as before. It's easy to verify this, and this function also supports computation of adjusted p-values using the step-down Dunnett procedure. To request this procedure, we need to set the proc parameter in the adjust p-values function to the keyword listed at the bottom of this slide.